Thank you for joining us for today's presentation by David Miles, Assistant Professor, UI Physics and Astronomy, with UI students Hannah Gulick and Josh Larson, who will speak to us today on an international rocket field school at the Andoya Space Center in Norway. I'm Dave Martin, ICFRC Board President and host for today's program. The FRC hosts community programs to address topics of international interest. We thank our members, volunteers, and interns for making these forums possible since the year that the Space Shuttle Challenger made its maiden flight, 1983. I want to acknowledge our university and community supporters, the University of Iowa's international programs, the University of Iowa's honors program, the University of Iowa Center for Public Policy, and the Stanley UI Foundation Support Organization for their financial support, and we thank today's special sponsors, Midwest One Bank and Mike Carberry. We also thank City Channel 4 for professionally recording our programs for cablecast on City Channel 4 or 118-2 and the UI Library's digital archives. David Miles is an assistant professor in the Department of Physics and Astronomy at the University of Iowa. Professor Miles is an experimental space physicist specializing in the development of next-generation spaceflight magnetic field instruments. He is the co-project leader of the Magnetic Field Instrument, MGF, on the Canadian Cassiope POP spacecraft, and is the instrument project leader for the miniature digital fluxgate magnetometer on the Ex-Alta-1 CubeSat. I practiced. Professor Miles was named one of Alberta's most influential people in the Next 10 by Alberta Venture Magazine in 2015. He received his PhD from the University of Alberta in 2017. Hannah Gulick is a sophomore from Spirit Lake, studying astronomy, physics, and English creative writing. She works on several research projects with the astronomy faculty. Hannah is currently working towards the goal of becoming a research astrophysicist. Josh Larson, who I think is on his way, David told me he's probably finishing a quantum mechanics exam.
You may never get here.
Yeah. Josh is a senior from Mount Pleasant, currently pursuing 2 degrees, a BSE in electrical engineering and a BS in physics. His ambition is to attend graduate school in pursuit of a PhD in space physics, with a focus on experimentation and instrument development for measuring space plasmas. Please join me in welcoming David, Hannah, and Josh.
So, good afternoon. Thank you everyone for the opportunity to talk here. So, I'm going to talk a little bit about a field school. I'm going to talk about how this field school came to be, how several countries came together to form this, what we're hoping to achieve. This is a school, adjust that a little bit, where we try to introduce students to space research, and in particular to rockets, with the goal of reaching out and trying to bring them into space-related science, space-related engineering, or the aerospace industry. So I'm going to talk a little bit about what the program is, how it came about, and what it tries to achieve. And then we're going to have an opportunity to have the 2 students from the University of Iowa that participated this year. These are actually the first 2 American students to ever participate in this international field school. And we're going to have them up and have them give us sort of their opinion of how the program went, what they learned, and sort of what their experience was traveling to what is actually a reasonably remote part of Norway and doing this reasonably intensive 5-day-long field school in northern Norway. So the program, I don't know how well it shows on the size of the monitor, was originally called CanoRock, which is the Canada-Norway Rocketry School. If my accent and the introduction hasn't given it away, I'm Canadian. Grew up on the west coast of Canada, and then for the last 10 years I've been in the University of Alberta in Edmonton, which is, so we're inside the Rocky Mountains and we're reasonably far north in Alberta. So there was a thing called the Transatlantic Science Week, which is held once a year, which is for participating countries on either sides of the Atlantic to get together and say, what interests do we as countries have that strategic interests, maybe from our region, from how far north we are, or from our position around the Atlantic, that could be addressed through scientific research, and in particular collaborative scientific research. So the Transatlantic Science Week is organized by the embassies in Canada, Norway, and the US, with a couple of other countries participating sometimes. And in 2008, it was opportunistic that they invited several space physicists from these different countries together and said, you know, is there anything that we have as a common interest that we could develop maybe better as a group than individually? And one of the things that came out was that in all of these countries, there's an aerospace program. There's space-related research being done, but it's actually really hard to attract good students into space research. And part of that, I think, is because space is seen as being very difficult, although it's no more difficult than, you know, many of the other hard science disciplines. But science is just, it's hard to get good students to come to space because they don't see it as an achievable career. So the idea that came out from some of the participating scientists in this was, could we put together a school where we would put undergraduate students together, we would give them a taste for what does it take to do a space mission? What are all the different people that you need? What are all the different skills that you need? What are all the different steps that you go through to see, starting from an idea, what does it take to build a mission, to get a piece of hardware up, and to prove to them that this is a thing that they could do, with the goal of then bringing them in and either getting them into graduate school or into the aerospace industry. So the mutual interest in Canada and Norway in particular at that time was, how do we get good undergraduate students into space and then get them into grad school, because we need to get them very well trained before they're useful in the industry. So that became the very first Canada-Norway rocketry school, or Canarock. So this was the advertising poster for it. So defy the odds, or defy the laws of gravity, study physics, engineering, and electronics, build and launch a sounding rocket in Norway. So sounding rocket is an old and antiquated term for a rocket that goes up and comes back down and never achieves orbit. And that might seem a little bit like, okay, what's the point of that? But there are certain altitudes that you can't get to any other way. So if you want to get to about 100 kilometers, which is sort of the edge of space, if you float on a balloon, you can float up to 30 to 35 kilometers. And after that point, balloons just don't float anymore, you can't get any higher. If you're in a satellite and you're in orbit, you can get down to maybe 200 kilometers, at which point the air starts getting thick for space, the satellite starts to drag, and pretty rapidly you deorbit your spacecraft and you crash it into the ocean somewhere. So there's this really interesting region of space that you can only get to on a suborbital rocket. So this is a rocket that goes up, goes through this interesting region of space, and comes back down. So when we talk about sounding rockets, what we mean is a rocket that goes up, does some sort of a scientific investigation, and then comes back down with ever actually orbiting the Earth. So the idea was we would bring together about 20 undergraduate students. We were going to bring them together from Canada, from Norway, because those were the partners at the time, and from a different and diverse collection of universities. We would bring them all to a rocket range, and then in the course of a week, we would have them build up a little rocket, where a little rocket here means, you know, sort of 2 meters tall, something like that. Put some instruments on it, launch the rocket, get some data home, and learn all the different things that you had to do to have one of these space missions. So a full space mission, but scaled down, and instead of a normal space mission, which might take, you know, $100 million in 10 years, we were going to try to do it in 4.5 days. Because that's the kind of scope that you can do with undergraduate students, because you don't want to pull them out of class for too long. We're not doing good undergraduate students a favor by yanking them out of class and having them miss so much that they then struggle academically. So whatever we do, it's got to be short. So we did this as a pilot program, and the pilot program worked really well. So then the Norwegians said, okay, let's renew this. We'll go for 5 years, and let's try to get a longer commitment, bring together some organizations, and see if we can do this for real. So the Norwegians, as it turned out, are very good at this. So the president of the Andoya rocket range wrote a letter to the Canadian ambassador to Norway saying, we would like to inaugurate, or have an inception, which is their word, for this very prestigious field school that we're going to do, and we would be honored if you would attend. And the ambassador said, well, that sounds like fun. Okay, I accept. I will come. So the Canadian ambassador to Norway is now coming to this inception, which at this point was just an idea. And as soon as the Canadian ambassador to Norway is coming, then the Norwegian ambassador to Canada has to come. So now the Norwegian ambassador to Canada is coming. But now that the ambassador is coming, the Canadian Space Agency has to send a liaison in order to brief the ambassador in what to say and how to put this in the context of space in Canada. Now, because the Canadian Space Agency is coming, the Norwegian Space Agency has to come. And this process went on for about 2 weeks until we had the rector of 3 universities, 2 university presidents, the mayor, some other very senior political figure. To put this in context, the Andoya rocket range where we're about to go is next to the city of Åndalsnes in northern Norway. It has a standing population of about 2,000 people. This was probably the most distinguished collection of oddball politicians and government agents that had been there in quite some time. And officially we launched the Counter-Rock program in January 2011. And standing in the center, he's the only one in the tie, is Canada's ambassador to Norway, John Hanford. So the moral of the story is if you want to kick off one of these international collaborations, invite the ambassador, because as soon as one ambassador starts, you have this arms race of officials. And pretty soon anyone who's anyone will be there. So this program kicked off. We signed a 5-year agreement. This was our representative, Marilyn Steinberg from the Canadian Space Agency, sitting in the center in the blue shirt. So the space agencies weighed in, they provided funding, and from then on in, twice a year, we would bring together 20 undergraduate students at the Space Center and we would run the field school. And the other advantage of having all of these sort of big and prestigious people in the room at the same time was we said, okay, undergraduate collaboration is good, but what we really want to do is get these students into graduate school, into research, into industry, so we should set our sights a bit bigger than that. So while we're there, why don't we have them sign a 6-way memorandum of understanding, recognizing that having collaborations and exchanges in space-related disciplines would be good, and that we should do it at the undergraduate level, the graduate level, and the research level. So these, because we had the dignitaries in the room, are people signing this grand, slightly motherhood and apple pie memorandum of understanding that says Canada and Norway both recognize the unique importance of space and our history of space research, and we agree to collaborate at undergraduate, graduate, and research levels. And so every time we try to add a component to this collaboration, we can point back at our memorandum of understanding and say, you know, we have already agreed in principle this is a good idea, and what we're doing now is just sort of fleshing out the details. So the schools that we're going to talk about today is the undergraduate exchange program. So this is 1 week, it's done at the undergraduate level, and it's always done in Norway. But we try to do, as I've talked about, this at several different levels. So in the Canadian and Norwegian system, the bottom of the rocket is the undergraduate program, and that's designed to recruit students. Then there's a booster in the middle, which is master's exchange, where we try to take students at the graduate, particularly in the master's program, and we send them back and forth from Canadian universities to Norwegian universities and vice versa for somewhere between 4 and 8 months. So they get a deeper introduction into the culture, but also they get to take courses that maybe aren't available at their home institution. So if there's a world expert in some particular topic, as part of this, you can pick up and go to another university and you can study under that person and come back. There's also a set of PhD field schools where we competitively select PhD students based on which ones don't run away fast enough. And then we lock them somewhere slightly remote, usually of 6 to 8 PhD students and 4 faculty members, and we lock them away for 2 weeks, and they're not allowed to leave until they've written 2 scientific papers. And this is a way of, for graduate students, teaching them a little bit on how to do research, but more importantly, how to write up your research and how to publish. And we found if you lock away a group of PhD students with their faculty members, particularly somewhere where the faculty members can't check their email, suddenly they become really interested in research. And at the end of this 2 weeks, you have, you know, journal quality, peer-reviewed scientific publications ready to go out the door. So the idea of this MOU was to support these exchanges at different levels and allow students to move both within institutions in their own country, but also between countries. This has all been written up in a little paper where we did some statistics on this. At the time we did the statistics, we'd had about 105 Canadian undergraduate students go through the program. Of those students, 77% were either in graduate school, had applied to graduate school, or made a credible statement that they intended to apply to graduate school. And that's pretty amazing. That's, at least 3 times more effective than any other intervention that I know of in this sort of area. Of that same cohort of students, about 40% had either applied for an internship or had applied to work in the aerospace industry. So we think that it works and it's a good formula. I started as a faculty member at the University of Iowa in August. So what I'm talking about here is an attempt to bring US or American participation into this exchange, because we know that it works, and this is an opportunity to take a formula, a program that's ongoing, and allow the University of Iowa to have a piece of this and to contribute to it. This is the recruitment poster for Canarock STEP. This is the PhD level, the school where we lock the students away and make them write papers. So the idea here is we're going to lock you away, we're going to have you write the paper, but by virtue of doing that, you are entitled to a scholarship where you can just have a block of money to go to one of the foreign institutions and study there for a month or 2. So if you have someone you'd like to collaborate with, someone who you think has a skill set, someone you could learn from, we have an incentive pot of money that says go international and study, and as long as it's going to one of the partners within the Memorandum of Understanding, we'll offer you this cash incentive to help defray your costs and get you to go. The last thing that we try to do with the program is when students have made it through, we try to get them involved in research. So this is a schematic of a mission called Maxidusty. So this was a full research rocket going to about 100 kilometers. And one of the conventional problems with rockets is you have a single rocket that goes up and comes back down. It's hard to tell the difference between something that is changing, that you sort of saw a piece of as you flow through, or something that is narrow that you flew through, because you only have one measurement point and you're moving. So Maxidusty was a technical demonstration of once the rocket is at altitude, it's going to release these little daughter payloads, producing what's called a string of pearls. So now you have a rocket and 3 satellites all moving together. So you try to have multiple measurement points moving together. And that was a master's student named Stefan, who, as part of his master's thesis, developed instruments for these 3 daughter payloads. So we had a student that went through the undergraduate program, the master's program, and then we also got them involved in the full scientific research side of this. So I'm going to move now to the field school, then I'm going to give the students a chance to talk. The place that we're going is in northern Norway, near to the town called Andoya. So if you go up the coast of Norway, just as it turns over, you are on a little island off the coast of, but sort of on coastal Norway, about as far north as you can get without going up deep into the Arctic Ocean to Svalbard. If you start from Iowa City, it's usually 5 airplanes to get to Andoya. So for some of our students who have not necessarily traveled internationally before, this was sort of a crash course on how to travel internationally. We were recruiting for a week-long course, so we usually fly out Friday night and we bring them back the following Sunday. And the idea is, over the course of 5 days, to build, test, and launch about a 5-kilogram rocket to an altitude of about 10 kilometers. New within the University of Iowa, we now have a course for field schools, so we also have an academic way of rewarding students who complete the program. And then this time around, we used internal university money to fund the students' participation. So, because as you can imagine, it's a reasonably expensive course to run, and we're seeking federal funding to turn this into an ongoing program. The application process is students apply by sending a CV or a resume. They send the transcripts, and then they have a 1-page essay basically saying, why do I want to participate? How would I meet the criteria of the program? And why am I the perfect and ideal candidate to go? So one of the ideas with this is, even for students who don't go or even before they go, this is essentially a grant proposal, which if they're going to go to graduate school, they're going to spend a lot of time writing grant proposals. So this is a chance as an undergraduate student to write what is basically a grant proposal. So even if they don't go on the program, they maybe have learned a little bit towards their career plan. So we had, I guess, about 15 applicants, and then we took the top 4, and they were interviewed by a panel of faculty members. We down selected the students, we bought them a set of airplane tickets, and then 5 airplanes later, you arrive here, which is the Andoya Space Center, previously the Andoya Rocket Range. And over the course of the week, our 2 students from Iowa joined students from the University of Alberta, Calgary, and Saskatchewan. And then this year, I think it was only the University of Oslo. in Norway, but previously there's been the universities of Tromsø, Bergen, the University Center at Svalbard, and the Technical University of, it's embarrassing, I can't remember their name. But each year we bring in a different cohort of students from different universities, we mix them together, and we take them out to the rocket range and they complete this course. So this was the Canarock class of January 2018. You may or may not be able to see it. They're holding a mock-up of the rocket they'll be launching. And this is the same cohort of students recreating the famous James Van Allen picture with the rocket that they're about to go fly. So with that, I will turn it over to, who talks first? I'll turn it over to Hannah. Thank you.
So hi, I'm Hannah Gulick, and like was introduced, I was able to attend this rocket school, and it was completely amazing. But first we're going to go through some of the groups so we can kind of explain to you how we built a rocket in 4 days. So there was 5 different groups, and each student was put in one of the groups. There was rocket physics, rocket system design, TM readout, telemetry, and payload integration, which may seem kind of like lingo, but we'll go through what each of those mean. So first we have payload, and their main job was just to take all of the instruments that we built. So we had like a thermometer, a pressure sensor, and then put them into the rocket. And this was a big job because obviously you have to put them in right and secure so they don't fall and break. But you also have to know where you're going to put them inside of the rocket, because some of the sensors couldn't be too close to the engines. Some of them needed like a hole above them so that they were able to see what was going on outside of the rocket. This also required learning how to solder, which is just melting wire together most of the time so you can connect things. And I know that coming from America, we'd already had this experience, but for the Canadian and Norwegians, they had to learn this while they were there. Another group was rocket systems, and so rocket systems built model rockets, which you'll find out Josh and I were both in rocket physics. We also built model rockets, and we kind of competed to see who could get the best model rockets. When they were building their model rockets, they got to test the engines for the model rockets, so we were able then to compare them to the commercial value. So what they sell them for, if they tell them they're going to go to a certain height, and then test if they're actually going to go to that height. And then after that, we can test our analyzation procedures. So you can kind of see here in this video, that's them testing one of the rockets, and the board kind of moved, which messed up our testing. And that kind of caused it to go lower than what the commercial value may have said. So by doing that, we were able to see that there's definitely error in procedure for testing. And then they also did some simulations to see where the rocket would go before and after launch. So getting to our part, we were in rocket physics, and our main job was to kind of model the rocket and then model its launch pattern. So this here you can kind of see is the trajectory of the rocket we think the rocket took after it was launched. We think it got to about 8.4 kilometers, which we aren't really sure what that is in feet. I can't really convert that, but it's pretty high. It's one of the highest rockets they've ever had. And this is really cool because we were then able to see where the rocket was going to land in the ocean, which is important because, as Professor Miles tells us, it's considered rude to drop your rocket on a boat. So we have to make sure there's no boats within the radius that the rocket's going to land in. So this was a really, really important job to know where the rocket was going to go. Something else we did was build model rockets. Like I said, this may seem kind of strange. It seems strange to me to go all the way to Norway to build a model rocket. I could definitely do that in the US. But then as you start doing it, you find out that it's an exercise in culture and teamwork. So we had Canadians and Norwegians on our team, and we were able to put together what we knew and then what they knew to get the best model rockets possible. I know coming from here, I had experience assembling things. I've worked on a couple satellite projects, so I was able to build the model rocket, and Josh was very good at optimizing the fins. But then we were also able to run simulations to see which fins would be best, how big the rocket should be for it to go as high as possible. And then another rocket, you wanted to launch it and have it come right back down as to where you launched it. So then we were able to see you would want it to go low then, which would make it go lowest. And then another rocket, we put an egg in it, so we wanted it to land really softly. So you didn't want that one to go high either, and you wanted a lot of parachutes on it. And this was a really cool project because we had mentors, and they were there for us if we had questions, but they didn't tell us what to do. So it was really up to us to build our model rockets and figure out the teamwork that was going to make our model rocket win in the competition. which I think we did win in the competition, but we don't have any data to back that up. In our group, we also got to launch a balloon, and the main purpose of the balloon is to get weather data before the launch so that we can know how windy it is. If you have a windy day and you're launching a rocket, bad things can happen. I know in another lesson, when somebody else went to the Canarock program, their rocket actually flew into the side of the mountain, so that's not ideal. So knowing what the wind is doing is really, really important before you launch your rocket. And our balloon had a GPS and temperature sensor in it, so we were able to track where it went and kind of see how high it went, which was interesting. Other roles in the program, there are launch positions. So I was actually elected principal investigator, which when I say elected, we put names in a Google randomizer and it picked my name, so that's how I got that job. And then there's also head of operation, who they kind of control everything. They talk over the intercom and tell people to start things like getting the rocket ready down at the Rocket Launch Center. And then principal investigator, my job was to tell the science report. So normally when you have a rocket you're launching, you want the perfect science conditions. And a lot of these rockets go into the aurora, and so you want to make sure you actually have aurora out, otherwise you don't want to launch your rocket because that's wasting a lot of money. Ours didn't really have any science goals, we were just trying to launch the rocket, but we got to make a mock-up of fake science goals, and I got to say that over the intercom, which is really stressful but really cool at the same time. And then this also taught communication. You're using an intercom, but then you also need to make sure that all of your different groups, your payload and rocket physics, are communicating and have the rocket done and ready to launch. And then this kind of leads into the international experience. I know working with the Canadians and Norwegians was a really, really cool experience because we talked a lot about our different educations. And so in Norway, sure, their education's free. In Canada, it's a lot different. They take about 7 more math courses than we do. It's kind of crazy. I don't know how they have time for all of it. But then you're also able to get ideas and motivation for the future. I know in Canada, they have this really cool program where the students lead a CubeSat, and they build a CubeSat, which is just a small satellite, but it's a student-led project. And I know here we've started to implement a student-led research project, which isn't quite to building a satellite yet, but we're doing a bunch of cool things, and maybe someday we could be building a satellite as the students. And also just motivation for grad school, opening up a lot of international connections. We're then able to kind of consider where we're going to go to grad school if we want it to be outside of America or inside of America. And finally, before I hand it off to Josh, I just have a video of the actual rocket launch, so I hope we can actually see this. And that was our rocket. It happened very fast. If you blinked, you missed it, but it was incredible to see our work being launched into space.
So, hi everyone, I'm Josh. Hannah kind of gave you guys a scoop about what we did before the launch and whatnot, but I'll give you guys an idea of some groups that maybe had a little bit more to do after the rocket launched or during the launch. So, this was one of the student groups called Rocket Telemetry, and they got to actually set up the whole communication system between the rocket and like the base back. So all the data that we got from the rocket as it was flying, these guys were in charge of making sure that came in crisp and clear. And I don't know, was the video that we showed the one that had the antenna in the bottom?
No.
Oh, okay. Yeah, so and actually during the launch, one of these guys got the job of steering a little antenna to track the rocket because it shoots off so fast that the regular antenna can't actually track it. And so that was one of the fun jobs that they got to do. Another group was the TM readout, so that stands for telemetry readout, and they had to basically take what the telemetry group got and turn it into things that we could actually like look at, read, and interpret. So a few fun things that they got to do was play around with learning Morse code, and they got this message from, there's this scientific base up on the mountain above, and they got a message from them that said hack the planet, which we were told is from an 80s movie, but none of us had seen it, so we were kind of lost on that. And a few more things about what our group did in the rocket physics, beyond just launching the balloon and the model rockets, we did these flow simulations. So the idea of the rocket physics group was to get an idea of what the physics dictating the rocket was. And so this flow simulation basically allowed us to simulate that. And so we were able to learn what the different things and colors in that plot there means, kind of at a top level without going into too much depth. But we learned a few things just from trying to interpret that between groups of students. So as you mentioned, we had Canadians, Norwegians, and the Iowa students. And everybody kind of has their different notations and standards that they run by. So one little bit that we ran into was when we were trying to talk about this plot here, we'd be like, well, one direction is the X direction, the other direction is the Y direction, and the last direction is the Z direction, right? Well, in the US, we would say that the kind of the direction of that arrow or the rocket's pointing would be like the Z direction. Well, to the Canadians, that was the X direction, and to the Norwegians, that was the Y direction. So just like little simple things of trying to talk about a plot that everybody looks at the same, but everybody interprets just slightly different, made for some interesting confusion in our conversations. We tried to launch the model rockets and have a competition with that. The first one that actually had the sensor got lost, unfortunately, so we don't have the results on that. But another little competition we had was simulating what the big rocket would do on the launch. And then after the launch, we all got our jobs to analyze the data back. So that's a little bit more about what we did, but some bits on things that I was able to take away from the program as a whole. Again, different backgrounds, whether it be that somebody was from Norway or Canada or the US, but also the fact that there were people who study computer science and engineering and then physics. And so working in an environment where not only you have differences in your culture, but also your expertise was something that I hadn't had much exposure to, and it was a really good learning experience for me. The students getting broken into the different groups so that we all had different responsibilities was also something that I had never worked on such a large project. So the rocket systems design was supposed to tell us how the rocket engines were supposed to perform. And we were supposed to take that data and then look at how that would affect the trajectory and things like that. Just merging all these smaller projects to build the larger project. And again, on the standards, getting confused about the coordinate systems, just trying to have a conversation was something that I'd never bumped into before. But one of the biggest things I think we learned was that building the rocket was hard, but then trying to talk about and work with the data with diverse teams ends up being even a little bit harder.
So this is kind of just a little blurb for the different experiences we had with the culture in Norway. So we actually got to go swimming in the ocean there because the students push you to do different things and step out of your boundaries. And it's called a Norwegian dunk, I think. And you have to go all the way into the Arctic Ocean and go all the way underwater, and then you come out. And we got a certificate that said we did an act of bravery. So that was really cool. And then most of it falls under the making connections with people. So I know we kind of stay in contact with our Canadian and Norwegian friends still. We have a Snapchat group and a Facebook Messenger, and we'll send videos and like what projects we're working on. But we actually got to experience downtown Oslo as well because some of the the students from Norway went to Oslo. And so we got to experience some of that culture, and that really preps you for grad school. Because I know I said this earlier, but I kind of want to go out of the country for grad school, so maybe Norway's an option. I know Professor Miles has a good track for going out of the country as well. And then the new ideas and motivation were a huge thing in international experience. And I think Professor Miles is back up.
So I'll just comment briefly on how we actually run the school and some of the guiding principles behind it, then we'll wrap up and we'll try to have time for questions. One of the things that we try to do with this school is not have it be a traditional school where you sit on a bench and somebody lectures at you for 8 hours a day. So in the course of the 4.5 days that we have them at the range, I think there are 6 hours of lecture. So we try to lecture only when it's necessary to either provide context or to give sort of a basic introduction. But the vast majority of the work we want, or the vast majority of the learning we want to be the students actually having the hands-on practical experience and taking advantage of the fact that they're in Norway and they're at a rocket range. So there was another guest lecturer from the University of Oslo doing a little introduction on this is what an instrument is. An instrument makes a measurement, and then, okay, let's send you out into the world for at least one group to go make some instruments. The other philosophy of the program is that we try to have all of the same roles as you would in a full scientific rocket campaign, but scaled down. So you can see 2 students looking at a little set of electronics cards that's maybe this big. So that would be all of the payload for the student rocket. The other picture is actually me from one of the previous scientific sounding rocket campaigns where now we are stacking together the electronics for a rocket that instead of being about 2 meters tall would be about 4.5 stories tall when you actually stack the whole thing together. So there's a difference in scale of the rockets, but the roles are the same, the place you're going is the same, and the processes are the same. The other way of thinking about that is on your right is a fully prepped scientific rocket. So that would be a little over 4 stories tall once you lift it vertically. It's tagged onto a rail, which is basically a crane, so you can lift the rocket into the launch position. And there are true students at the same facility and the same launch rail, being able to see the facilities that they would use if they were doing this for real on a scientific rocket. The first scientific rocket that I did was ICI-4, which was studying how space weather can interfere with GPS navigation. So if you're the principal investigator, you're the lead scientist for one of these missions, you've had the money for the mission, you probably have worked on the rocket for 3.5 years, there is a point where you have to make the call to launch the rocket. And when you say go, you probably spend $4 to $5 million. So at that point, you need to be confident that the technology is working, the instruments are working, the weather is working, and there's something worth measuring up above you. So on one side, we have Professor Johan Moen at the University of Oslo in the process of spending $5 million launching a rocket. And in the other one, we have Hannah, who's actually starting to look a little bit nervous in that picture. As she, in the appropriate point in the countdown, had to make a call or a report on the scientific conditions of the launch. To give a little bit of context on the sorts of people that do these missions, so I mentioned it's about 5 airplanes to get from here to the Andoya rocket range. By this point in the scientific mission with Joran Moen from the University of Oslo, we had been on the range for 3.5 weeks. And there's not a lot of airplanes that go into and out of Andenes. And we couldn't book a return airplane because we didn't know when we were going to launch the rocket, because we had to wait for the scientific conditions to be right and the weather to be right. From the point that he says go on the rocket, there's about 3 minutes in the countdown to the actual ignition point, at which point the rocket takes off and starts flying. It has about 6 minutes to altitude, then it will do its science, then it will land in the ocean. So he says go, and then he looks very attentively as we go from 3 minutes to 2 minutes to 1 minute to launch, and the whole building shakes as the rocket takes off. At which point, I was glued to my little readout, checking the instrument and making sure that everything was looking perfect, working perfectly, and we were going to get the absolute perfect data back, and I looked over. And Professor Moen has his laptop open and is booking his airfare to go home. Because there's nothing he can do at this point. The rocket's going. It ain't coming back. But he got on the next airplane. And in fact, he got the last seat on the next airplane. Whereas I got a red eye 3.5 days later. So the people that do this for real and have done it several times are very practical people. The other sort of philosophy that we use in the school is rocket science is hard. There's going to be a lot of failure. You have to learn how to recover from failure. So it was mentioned that we had this one steerable antenna which was going to track the rocket to try to bring data home over a radio link. So the idea is, as the rocket comes off the launch rail, it's moving so quickly that the automatic tracking can't quite keep up with the rocket. So we were going to have a team of students, actually with 2 little wheels, steering another antenna to try to get data from this early part of the launch. Which is a good idea, and it's a good opportunity for what we call mitigated failure and recovery. So here we are.
20 seconds.
20 seconds.
20 seconds.
So the white thing in the center is the antenna. You'll see it steer in just a second, and the rocket's going to go up in the background. 5, 4, 3, 2, 1, 0. And here goes the antenna, and the students are very industriously tracking where they think the rocket is supposed to be. But there's a fundamental problem. And this is, it turns out, is actually a very useful exercise for the students. This is why you have more than one antenna. Because sometimes things don't go quite the way that you hope they will. Similarly, the picture in the top is 2 students who were supposed to build an instrument that was going to take hyper-detailed measurements of the magnetic field. So it was going to have, 500 possible different values of fine gradients of the magnetic field. And when they got their data back, they discovered that they had an instrument that could say the magnetic field is up or the magnetic field is down. Which, for those of you that are good at math, is 2 possible values of the Earth's magnetic field. So the other thing that we try to make the students do is peer instruction. So in the bottom, these are the students who have now had probably a long and fairly sleepless night trying to figure out what went wrong. And they are now presenting back to the other students on, this is what we tried to do, this is what we actually did, this is what we think went wrong, and here are our lessons learned. I actually think that's a very valuable experience for a student. You may recognize some people here and some of what they're presenting, but there's always an opportunity for the students to present their work and then to get feedback from their peers. So, in essence, the student rocket program is intended as a crash course, 4.5 days, in what does a scientific mission to space look like, what are the types of skills you need, what are the types of people that you need. It's a teaser to get students involved so that we can get them into graduate school and into the aerospace industry. Hopefully this was the first time that University of Iowa students went. Hopefully students will be going, at least once or maybe even twice a year into the foreseeable future. And a great many institutions and funding agencies are required. I'm not going to go through the list, but hopefully this will be an ongoing fixture at the University of Iowa, providing opportunities for our students. Thank you.
Okay, I'll start with this. This is probably for, I assume for Hannah or Josh. What non-scientific things did you learn? For example, culture of Norway, or, I'm not sure, culture of Norway, anything non-scientific.
So we got a lot of Norwegian culture while we were there. We got to see the Northern Lights, which was incredible. We also learned that they eat a lot differently than we do. They eat about 6 times a day. It's all bread and meat too. Do you have any?
So it was interesting to learn how bilingual all the Norwegians were. One of the first days we were there, something interesting kind of happened. So we were all kind of sitting at lunch and chatting, and this group of Norwegian students had gone from, it was 3 Norwegian students had been talking in Norwegian, but then thought to be polite they'd talk in English so that everybody could understand the conversation. Well, then their conversation went on to talk about apartments in Oslo, and none of us are familiar with what apartments in Oslo are like, but they continued this conversation that was very, very Norwegian-centric in English, so that we could understand, but without realizing that the conversation was kind of isolated to the Norwegians. And it was just, the term that one of our friends used was that Norwegians often get language confused. So, and I thought that was very interesting.
Another really cool thing is when you get to northern Norway, they have roads, but a lot of time there's snow on the roads, and it takes about 4 hours to follow the roads when you could just take a plane that's 45 minutes. So they kind of use planes like we would use buses here, and they kind of, I think they have plane passes like bus passes, and they just hop from plane to plane to get to different places.
Okay, so this question, did you build rockets out of preformed panels, etc., or more basic materials? Like, so how did you build the rockets?
So the student rocket was pre-built out of like a big carbon fiber tubing, and I think that was commercially procured. Yeah, so that was bought. The little model rockets were like cardboard tubing and then plastic and balsa wood fins. So we didn't build anything exactly from scratch, but those were kind of the materials that were used.
Okay. Anything else? Does anyone investigate pressure inversions in the upper atmosphere and relate them to sunspots?
There is a lot of meteorological research which is done at the Andoya rocket range and at a place called Alomar, which is a LiDAR observatory for doing atmospheric research, which is just sort of up the local hill from the range. I can't speak in detail about any of that because it's not my area of expertise. I will say that it makes it an especially pretty place to visit because you go out at night and you're on the coast of Norway, there's the ocean rolling in, you're framed with the mountains, there's probably the northern lights overhead. But at the top of the mountain, there's a LiDAR observatory, which is where you shoot laser beams up and then you look at the light that's being bounced back from sort of as the lights hit clouds and different things in the atmosphere. So you go out at night, you're on the beach in Norway, everything's covered in snow, there's mountains, there's clouds, there's the northern lights, and then there's green and yellow laser beams going back and forth in the night. So it's a pretty unique place to visit. They do a lot of atmospheric research, but I can't speak to that in any detail.
Oh, thanks. Well, I'll start. So this says Lockheed Martin would hire you on a New York second. Are you interested? Anybody?
You guys gonna go? I would not, no. The University of Iowa has been very generous to me, and I'm very happy here.
Once you finish, yeah. Okay. I've got several questions here, mostly for the students about, I'll save that one for last. Well, I guess this is more for David too. Are there opportunities for local high school students to engage in any of these or other programs like this?
So I don't know what's available this year, but there was a program probably 2 years ago, which was actually held at the same place, the rocket range, called CanSat, where they brought high school students out, but before the students could go, they had to build an experiment that fit in a pop can. And then they loaded all of the pop cans into one of these rockets with a little parachute on the top of each of the can. And then they sent the rocket up, and at 10 kilometers, they ejected these CanSats, which is like a Coca-Cola can with a parachute on the top of it. So it was an opportunity for high school kids to build something at their own high school, load it into the can, and then go to Norway with the can to participate in this sort of international high school summer program where they would go fly these little experiments that they built. So if the person who asked that question wants to come talk to me at the end, I can try to dig up the link to that, because that happens every few years.
Okay, I'll make this the last question for the students. Did you really, really enjoy breakfasting on lutefisk?
I think that was the one bit of Norwegian fare we didn't get to try. Yeah, unfortunately, there was no lutefisk about. So
Caviar for breakfast.
yeah, there was caviar, reindeer, and a few other things. But
For breakfast.
they actually serve pretty similar things for breakfast as for lunch.
Okay, I'll conclude our program now. A big thank you to David, Hannah, and Josh. We want to thank again our sponsors, University of Iowa's International Programs, University of Iowa's Honors Program, University of Iowa Public Policy Center, and the Stanley UI Foundation Support Organization for their support. And today's special sponsors, Midwest One Bank and Mike Carberry. And we thank City Channel 4. David and Hannah and Josh, as a small token of our appreciation, we're going to present each one of you with our coveted Iowa City Foreign Relations Council mug. Thank you again for joining us. We are adjourned.